We click, we type, we swipe all day long, and stuff just happens, right? But have you ever really stopped and wondered what's going on under the hood? Well, in this explainer, we're going to pull back the curtain on that magic and take a look at the incredible machine whirring away inside your computer. Let's get into it. I mean, really think about it for a second. You click an icon, and this huge, complex program just springs to life in a flash. It feels like magic, but it's actually this incredibly elegant, logical dance of components. And we're about to map out that entire dance, step by step. So to really get this, we've got to start with one big idea, the difference between a computer's design and its actual physical parts. The best way to think about it is like building a house. First, you have the architect's blueprint, and only then do you have the physical bizzing made of bricks and wood. In the world of computers, we call these two things architecture and organization. Okay, so architecture is the what. It's the high-level plan. It's all about what the computer is supposed to do. It answers questions like, what kind of math can it perform? How does it handle data? Then you've got organization, which is the how. This is all the nitty-gritty, how it's actually built. So the architecture might say, this computer must be able to add two numbers, but the organization is what decides the specific circuits and wires to make that addition actually happen. Computer architecture is basically that abstract blueprint. It's the official rule book for the hardware. This is what a programmer actually sees and interacts with. The set of commands they're allowed to use, the little bits of super fast memory called registers, and the types of data the machine can understand. As long as the developer plays by these rules, their software will work. It doesn't matter what the machine is physically made of. And then you have computer organization, which is the physical reality. It's the nuts and bolts, the actual circuits, how the ports are connected, all that stuff. Now, here's the really cool part. You can have totally different organizations that follow the exact same architecture. Just think about Intel and AMD. They build physically different chips, but because they follow the same architectural rules, they can both run the exact same software. All right, so we've got our blueprint and our building plan. Now let's roll up our sleeves and actually start putting the pieces together. We're going to look at the three main parts that make up the heart and soul of any modern computer. First up, the absolute star of the show, the Central Processing Unit, or, as we all know it, the CPU. This is, without a doubt, the brain of the whole operation. It's this incredibly complex little circuit that's responsible for executing all the instructions from your software, doing every calculation, and making every decision that makes your programs work. But, the CPU isn't just one single thing. It's really two key players working together. First, you've got the Arithmetic and Logic Unit, the ALU. This is the computer's powerful calculator, handling all the math and all the logical comparisons. Then you've got the Control Unit, or CU. Think of it like a traffic cop or the central nerve center. It doesn't do the math itself, but it directs the flow of information across the entire computer, telling the ALU, the memory, and everything else what to do and exactly when to do it. Of course, a brain needs a place to work, right? That's where the memory unit comes in, which you probably know as RAM. Think of it as the CPU's personal workbench. It's not for long-term storage. That's your hard drive. This is the temporary workspace, where all the programs you're currently running and the data they need are kept for super fast access. Okay, so we've got our components: the brain, the calculator, the traffic cop, and the workbench. Now for the fun part. Let's see how they all team up to actually get something done by tackling just one little item on the computer's massive to-do list. That whole to-do list is made up of what we call computer instructions. And each one is just a teeny tiny, super specific command for the CPU. Something like add these two numbers together, or move this piece of data from here to there. What feels like a single click to you is actually to the computer a sequence of millions, sometimes billions of these tiny instructions. The way the CPU chews through these instructions is in this constant, relentless cycle. Seriously, it's like the heartbeat of your computer. First, the control unit fetches the next instruction from memory. Then it decodes that instruction to figure out what it's supposed to do. And finally, it tells the right parts, usually the ALU, to execute the command. Fetch, decode, execute. Over and over again, billions of times every single second. It's wild. But wait. How does the CPU know which instruction is next in line? Well, it has this little bookmark, basically. It's a special high-speed spot inside the CPU called the program counter. And its only job, its entire purpose in life, is to hold the memory address of the very next instruction. That's how it keeps everything running in perfect order. Now, there's a catch. There's always a catch, right? CPUs are ridiculously fast. But going all the way out to the main memory, the RAM, to grab data is, relatively speaking, pretty slow. If the CPU had to just sit there and wait for RAM every single time it needed something, your super fast computer would feel like it was crawling through mud. So to fix this, designers came up with a really clever system, a hierarchy of memory. Think of this hierarchy like a pyramid of speed. At the very top, you have those CPU registers we mentioned. They're the absolute fastest memory you can get, but they're tiny and crazy expensive. Right below that, you have cache memory. Then comes the main memory, or RAM, which is much bigger but a bit slower. And way down at the bottom is your huge but much slower hard drive. The rule is simple. The higher up the pyramid you go, the faster, smaller, and more expensive the memory gets. The real secret weapon in this whole setup is the cache. The best analogy is a little countertop right next to your main workbench. Instead of walking over to the big tool shelf, that's RAM, for every single thing you need, you keep the tools you're using most often right there on the counter for instant access. The cache does the same thing. It holds copies of the data the CPU has been using recently, betting that it's going to need that same data again any second now. So here's how it all pays off. When the CPU needs a piece of data, it looks in that super fast cache first. If the data's there, bam, that's a cache hit, and it gets the data almost instantly. This is what makes your computer feel snappy and responsive. But if the data isn't in the cache, that's a cache miss. Then the CPU has to take that slow trip all the way out to RAM to get it. That's that tiny little stutter or moment of lag you sometimes feel. The whole point of the system is to get as many hits as possible. And of course, engineers have a way to measure this. It's called the hit ratio. It's just a simple percentage. You take the number of times you found what you were looking for in the cache, and you divide it by the total number of times you looked for something. Modern computers are designed to have incredibly high hit ratios. We're talking over 95%, because that is the absolute key to making them feel lightning fast. So we've built this incredible system of processors and memory and these clever caches all working in harmony. But it turns out the very design that makes it all possible also creates this one huge fundamental limitation, a problem that engineers are still trying to solve today. This problem is called the von Neumann bottleneck, and it all boils down to something simple: traffic. See, the CPU and the memory are two separate things, and they're connected by a data highway. The problem is, both the instructions on what to do and the data to do it with have to travel on that same single highway. This creates a traffic jam. The CPU, which is blazingly fast, often ends up just sitting there twiddling its thumbs, waiting for instructions or data to arrive from the slower memory. And that leaves us with this really fascinating challenge. We've come up with brilliant workarounds like putting multiple processor cores on a single chip, but as our demand for computing power just keeps exploding, the fundamental problem is still there. How do we solve that traffic jam between the processor and its memory? The answer to that question? Well, that's what's going to define the next generation of computers.